Hi everybody, today we're just going to do a quick review of significant figures in scientific notation, two topics that you should already be familiar with from previous math or science classes. So the objectives for this lesson are to be able to express measurements that we take in the lab with correct significant figures, and to express measurements using scientific notation. We'll be using a lot of numbers in our calculations in class, and you want to make sure you know when they're expressed in scientific notation what to do with them. Let's start first with significant figures. Significant figures are used to show us which digits in a measurement are known with certainty. So for example, if you were asked to measure the length of this ruler in lab with a metric ruler, it's in centimeters, you might come up with a different way of expressing the length. So let's look at each way that you possibly could express it and see which is the best, which we can do with the appropriate number of significant figures. If you look at it, you may say, first of all, it's about 8 centimeters. All right. First of all, you know looking at that pencil that it's longer than 8 centimeters. So 8 centimeters is really not a good measurement to report it with. You might go down and you might go, okay, well, if I look at the divisions between 8 and 9 centimeters, there are 10 of them. So it must mean that each one of those small divisions between the 8 and the 9 means a 0.1 of a centimeter. You would be right. So you could look at that and you might say, that's all the way, that's 8.3 centimeters. I know it goes past the third little division, but it might go all the way to the fourth. It's not exactly at the third division. So you might want to say 8.3 centimeters, or you might want to be able to say, well, it's a little bit more than 8.3, but it's not quite 8.4. And that's where you take an eyeball, or you make a estimate of where it fits within the 2 points that it falls. So if I look at this, I say it falls about halfway through, about 8.35 centimeters. The last one is a little bit unrealistic, I hope. This looks like something that comes out of somebody's calculator. There is no way to measure with that ruler that type of measurement. 8.34589135569 centimeters is just not doable. Significant figures have to do with the precision of the instrument that you use to measure with. You can only measure to the precision of the instrument. So this guy measures all the way down to the millimeter. So you can measure all the way down to the millimeter with a little bit of uncertainty or a guessing about how it falls in that millimeter range. So being able to say something like that measurement is just totally unrealistic. And if you've got a measurement like that that you calculate in class with a calculator, that's a little unrealistic to present too. So you may have looked at this and you may have said, okay, it's probably one of these two, 8.3 and 8.35. According to the rules of measurement and using significant figures, this guy is my best measurement. And let's see why. All right, when you measure with significant figures, they help you, like I said, record the amount of exactness or the precision of the tool used to make the measurement. So when you measure with appropriate significant figures in the lab, you record as many digits of the measurement that you know with certainty. So I knew with certainty that that pencil was at least 8.3 centimeters long. Not quite 8.4, at least 8.3. And then I take the best estimate of reading one more digit as accurately as possible. Hopefully those words precision that I use about the precision of the tool and accuracy are words that are familiar to you. Remember, precision has to do with the tool and how well you can measure. Accuracy has to do with how close you are to the right or correct value. So that's your process for measuring with significant figures. A couple of you may ask about using significant figures in our calculations in class. I am not going to worry so much about significant figures when we're doing problems. Problems come out of the book, problems come out of worksheets, problem comes out of different examples. We always don't really know about measurements to say whether or not those are really taken with significant figures. So when you work problems in class, I'm not going to be asking you to follow the rules of significant figures in order to be able to express your answer. But I would ask that you be reasonable. If your Values that you plug in or substitute are to the ones place or the tens place. Round your answer to the ones place or the tens place. Don't give me 5 digits after the decimal point or all the digits after the decimal point that your calculator gives you. It's just not reasonable. You cannot say that answer even without even thinking of significant figures. In the lab, when you do make measurements, though, I am expecting you to be able to record measurements appropriately using significant figures. All right, so when you're reading significant figures, somebody else's data, or recording them, you do have to watch. There are some rules, and these are the rules that you should have already learned maybe in chemistry. First of all, this is the easiest rule. All non-zero digits are significant, meaning any digit that is 1, 2, 3, 4, 5, 6, 7, 8, 9, it automatically is significant. Any zeros that are between non-zero digits are significant. So, for example, a number like 909. All right? The 9 and the 9 are significant, so as a result, this 0 is also significant. It indicates that there were no tens in my measurement. And the simple fact that I measured all the way down to the ones place tells me that that non-existent tens place is actually significant. Here's where it gets a bit dicey for everybody about those extra zeros, those zeros that are either at the beginning of a number or the end of a number. What's the rule with those? So here's a good way to remember. Any final or trailing zeros, meaning zeros that come after a series of significant digits, are only significant if they are in the decimal portion of the measurement, meaning to the right of the decimal point. So these are your numbers where you have something like 0.0020, all right? That 0 at the end, this guy right here, is significant. It's saying I measured all the way down to that precision, and there was no value in that place. Zeros that act as placeholders, those at the end of a whole number or those at the beginning of a decimal, like these, that are less than 1, are not significant. So in this case, these would not be significant. Here, this 0 is just a convention. I generally put a 0 in front of my decimal point if I'm giving a number that is a decimal, just to make sure that decimal point is really highlighted. But if this one, if I had a number, say, for example, like 20,000, all right, all of these zeros that are placeholders would not be significant. So essentially, if you think about it, those zeros that either get us to our first significant figure, either going right or left from the decimal point, are never significant. Okay, so that's pretty much significant figures in a nutshell. Let's move on to scientific notation. All right, first of all, scientific notation, you've probably used it before. Why do we use it? Well, measurements vary greatly in magnitude, a word you're going to hear often during the year, so make sure you get the idea of what it means. It means the size of things. So if you look at measuring the length of your hand, if you look at measuring the width of your hair, one piece of hair, if you look at the distance from the Earth to the Moon, the measurements of that, all three of those lengths, vary greatly. So when we start expressing really, really small measurements or really, really large measurements, we like to be able to use scientific notation. And you may say, why? Well, let's look at this. If you look at these two pairs of numbers, out of each pair, which one is the easier to read? Or which one's the easier to write? Or which one's the easier one to put in our calculator? Right. In most cases, it's this guy. If you're familiar with your scientific notation, you're going to know that if this guy is a positive number, that means I'm adding a lot of zeros. I have a really big number. The bigger that exponent gets, the bigger the number gets. If this guy is a negative exponent, the more negative, or the larger the negative number is, the smaller the number gets. So it's a really good way to have an instinctual feeling about how big or small a number is. So now, how do we start recording measurements in scientific notation? Not always does our tool match how we want to report our measurement. So sometimes we have to watch about how we record and then represent our information using scientific notation. So you always still record your measurement with the correct number of significant figures. Again, this is going to depend on your tool. But sometimes your tool, say for example, you may have used a caliper in another class where you record really, really, really small lengths. But when you have to take that measurement and then put it into an equation to figure out something else based on that, it may not be able to be in that unit of measurement that caliper gave you. So as a result, you might have to convert it into a standard metric unit. And that's where you start worrying about how I express it with scientific notation. So if you're given the measurement, the first thing you want to do is be able to move the decimal point so that there's only one significant figure to the left of the decimal point. Remember, in standard scientific notation, you have something, a number, all right? You have coefficient times 10 to an exponent, all right? Where this coefficient here has to be between 1 and 9. It can be 9 point something, but remember, it can't be any greater than 10. And then you finally express the movement of the decimal point here using that power of 10. Let's look at a few examples. Right, let's rewrite 300,000 meters in scientific notation. This is the way I do it. The first thing I do is I place the decimal point. Let's take my number and rewrite it. I place my decimal point so that the number is between 1 and 10. You can also think of this as I place the decimal point so that there is only one significant figure to the left of it. That means it goes right here. So this number is now going to become my coefficient for my scientific notation. It's going to become 3. All right, and why is it going to become 3 and not 3.0000000? It's because if I look at this original measurement, none of these zeros were significant. So I don't put them in my scientific notation. Right? Then I need to figure out what my exponent is going to be. The way I do it is I go, well, to get back to where my decimal point really was, I had to go 1, 2, 3, 4, 5, 6, 7, 8 decimal places to the right. Right? And to the right is a positive. That's how I do it. Let's look at another example. 3.00, I'm not even going to say them. All those zeros, 394 meters in scientific notation. I'm going to take a bit of a shortcut here. I know this 394 here is going to be my coefficient because they're the only digits in there that are significant. I place my decimal point so that the number is between 1 and 10, or there is only one significant digit to the left of the decimal point. And if I think about where that is in this number, go right here, I figure out how many times I have to move the decimal point to get to where the decimal point really is in the number. So let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this guy will become 3.94 times 10 to the negative 12. Okay? You may have a different way of doing it, and whatever works for you is fine. That just happens to be the way I do it. But you can see now that these numbers are much easier to read and maybe much easier to put into your calculator if you're doing some calculations. All right? Let's look again, just one more example, making sure that we're okay, because we'll have to watch here about our significant figures. All right, let's look at this guy, rewriting 0.003710 meters in scientific notation. Here again, just like I did in the last one, I'm just going to take the chunk of significant figures that I know are going to create my coefficient, In this case, it's all of these. That 0 at the end here is significant, so it has to go in my coefficient. I'm going to place the decimal point so that the number's between 1 and 10, or that there's 1 digit to the left of the decimal point. And now I'm going to determine my number of times I have to move my decimal point. So I have it here. I go 1, 2, 3, 4. To the left, which is negative for me, and that would give me that measurement in scientific notation. Scientific notation is a great tool not only for expressing those large and small numbers, but it's also a great tool for being able to determine those significant figures when the zeros are the problem. So if you see something like this, you know that that 0 has to be significant, because the whole point of scientific notation is to do that multiplication or division by 10 that we are doing when we are moving from the decimal place. So it gets rid of all those zeros, either going to the left of the decimal point or to the right of the decimal point, to get to our first significant figure. All right, and then last but not least, sometimes you might want to go from scientific notation to standard notation. So here, if I want to rewrite this, I take my 1.605, I take my coefficient, and then I simply move my decimal point the number of places that that the exponent tells me. It's a positive number, so I move my decimal point to the right, just like I'm working on the number line. 1, 2, 3, 4, 5, 6, 7. Here is where my decimal point really goes in that number. And any of these little guys, I fill back in with those non-significant zeros. Okay, that's about it. That's a review. A good clue, just to make sure, if you are looking at numbers that are in scientific notation, just remember, if the exponent is positive, the number is usually much larger than 1, and if the exponent is negative, the number is usually a fraction, meaning it is between 0 and 1. Okay? If you have any questions, please come to class prepared.